In this video, we're going to talk about how to do some inference on a population mean, specifically hypothesis tests and confidence intervals, using the t-distribution. So let's get started. We'll connect this first. Okay. So a little bit of review before we jump right in. So the central limit theorem is something that we learned about way back, like the first month of the class. And what it told us was this about the sampling distribution. So assuming our sample size is large enough, the sampling distribution of the sample mean is approximately normally distributed with mean mu, standard deviation, sigma over the square root of n. So what that did was give us a way that we could think about what samples might be generated from a particular population. We used that to flip the switch and calculate a confidence interval. So given a sample, what can we say about the population? So let's dig into estimating that population mean mu. There's a problem with the derivation that we've got here. If we would like to estimate the population mean mu, we unfortunately don't have all the information. We don't actually have the standard deviation sigma. So what do we do? Well, one option would be to replace that population standard deviation sigma with the sample standard deviation s. The problem here is that once we do that, this isn't normally distributed anymore. This introduces some extra variation into the picture. We're estimating two things from our sample, not just one. We're using our sample mean to estimate our population mean, and we're also using our sample standard deviation to estimate our population standard deviation. So things just aren't normally distributed anymore. However, we do have a new distribution that we can introduce called the t-distribution that captures that variability. So think of a new test statistic. This is actually one that we've used before. It looks a lot like a z-score because really we're just measuring the distance, specifically how different a sample is from some population. So this new test statistic, which we'll call t, takes the sample mean, subtracts the population mean mu, divides by s over the square root of n. Now we say that this new statistic follows a special distribution called the t-distribution. Here's what the t-distribution looks like compared to its parameter, degrees of freedom. Now, degrees of freedom is a measure of how much information we have. So in the legend of this graph, as you see df go up, that increases with the sample size. So darker blue lines indicate bigger samples. The bigger that sample gets, what do we notice? Well, the dark blue lines are really close to the normal distribution in red. So for large samples, the t and the normal distribution really aren't that far off. However, for small samples, the distribution's wider on the ends and shorter in the middle. There are some properties of this new t-distribution. First, it's symmetric. It's a bell-shaped curve. It's got a very similar shape to a normal distribution. It's just a bit fatter. So the ends are a bit thicker, the middle's a bit shorter. So what that tells you is that values that are farther from zero, values of t that are out here or out here, occur more often. We're more likely to see unusual t-values. Because this distribution is a little bit wider, it helps account for that extra variation that we've now introduced into our sample. So that's really why we like this t-distribution. The t-distribution is always centered at 0, so we don't have to think about where the mean might fall because we know where that's going to end up. It has a single parameter called the degrees of freedom. So what the degrees of freedom actually represent are the sample size, specifically the sample size minus 1. So a sample of, say, 3 observations would have 2 degrees of freedom. The bigger this sample size gets, the closer the t-distribution gets to the standard normal distribution. All right, so how can we use this t-distribution? Well, we can use this t-distribution to help us find a confidence interval. The way we'll do that is pretty similar to the confidence intervals that we already know how to use. So we'll take our sample mean x bar, we'll add and subtract something times the standard error of the sample mean. That something is now going to come from the t-distribution rather than the normal distribution. Because that t-distribution changes depending on the sample size, we need a convenient way to find that t-star value, so we'll use the qt command from R. So here's an example of how that qt command actually works. Let's say we have a sample of 10 observations and we'd like to find a 90% confidence interval. This qt function has two inputs. It's got a probability and a degrees of freedom. So we'll start with the degrees of freedom first. This is just the sample size minus 1. So if we have a sample of 10, we'll input 10 minus 1 or 9. The probability is a little bit more tricky to calculate. We can't enter the 90% confidence interval directly because that represents middle probabilities. To get the t-values that cut off those middle probabilities, here's what we do. We take an approach very similar to what we did when we worked with the normal distribution originally. We figure out how much goes up to that point. So if we have, say, a 90% confidence interval, alpha then is 10% on the left-hand side of this equation. So to find this, we'll take 1 minus 10% over 2. So 1 minus 0.1 over 2. That will give 0.95 for the p. Let's say that we want to find t-star for a sample of 15 observations. Our degrees of freedom are then 15 minus 1, or 14. For a 99% confidence interval, 1 minus alpha, alpha must be 0.01. So 1 minus 0.01 over 2 gives us 0.995. So that's how we get this p. That means that in our confidence interval formula, we'll add 2.97. So let's take a look at how we might use this. So outside of currently living cells, one of the most common places that you find DNA out in the wild is on the ocean floor. Essentially, organisms swimming in the ocean die, DNA falls to the ocean floor as the organism decomposes. A random sample of 116 locations around the world gave the following information. So we have a mean and standard deviation for the DNA concentration on the ocean floor. We'd like to use this to find a confidence interval for the mean by hand. I will apologize to those of you who would like to know the units. Unfortunately, I do not know those off the top of my head. So we've got the mean, we've got the standard deviation. The next thing we need is that t value. We have 116 locations, so the sample size minus 1 is 115. For a 95% confidence interval, we'll take 1 minus 0.05 over 2, get 0.975. This is very close to what we used in a 95% interval based on the normal distribution. So to do this calculation, then we'll plug everything into the formula. The final confidence interval we get is this. So our confidence interval ranges from about 0.24 to about 0.31. Interpreting this confidence interval based on our data, we're now about 95% confident that the population mean DNA concentration on the ocean floor is somewhere between 0.2449 and 0.3113. Let's take a look at another example. So a study in the Journal of the American Medical Association took 3 groups, each with 25 subjects, and wanted to measure how the volume of the hippocampus was related to a history of concussion. So the first group consisted of healthy people with no history of brain trauma. The second group consisted of college football players with no history of concussion. The third group was college football players with a history of concussion. So here's the data. We have a column called group that contains the control information, column called hippocampus that contains that hippocampus volume, left hippocampus, years playing football, these are 0 for the control, and then a cognition score that wasn't measured. Here's what this data looks like. So for the control group, which is plotted in orange, we see a much wider curve that is more on the heavier side of the hippocampus volumes. Football players with history of concussion are the lowest, and football players without a history of concussion are kind of right there in the middle. So we can create a table summarizing the total hippocampus volume for the control group. These are the non-football players. Let's use this to calculate a 95% confidence interval. This may be a new function. Instead of using the skim library, an alternative is the favstats function. So favstats stands for favorite statistics. We can take the favstats function, apply it to the hippocampus variable, split it into groups based on group, and our data set is the football brain data set. Same statistics. Here's the mean. Here's the standard deviation. Here's the sample size. Last thing we need to calculate this confidence interval is the value from the t-distribution. Our sample size is 25, so degrees of freedom are 25 minus 1. For a 95% confidence interval, you'll use 0.975 to get that endpoint. So down in our calculation, we'll plug everything in and end up with a result of 7,159.3 to 8,045.9. We're 95% confident that the mean total hippocampus volume for all non-football players or all control type players would fall into that range. Let's do 2 more, and I'll leave the details for those of you at home to try. So if you'd like to calculate the volume for all football players without concussions, the result you should get is right here. The confidence interval for all football players with concussions, you should get this result. Notice these confidence intervals are significantly lower. So it looks like football players with a history of concussion do have lower brain volume. So let's move away from confidence intervals into testing. So how can we do a hypothesis test using these sorts of procedures? So the same 4 basic steps apply. Step 1 is to write a null and alternative hypothesis. So our null hypothesis is some statement mu equals mu 0. The alternative might be less than, greater than, not equal to, depending on the research question, of course. Step 2 is to compute the test statistic. So based on our data, we'll calculate some test statistic. Essentially, we'll just measure how far the data is from the assumed mu 0. We'll let R handle this calculation, but here's the formula if you'd like to do it by hand. Then from that test statistic, we'll calculate our p-value. Again, remember, this is a probability. So this is the probability of observing data as or more extreme as our sample, assuming the null hypothesis is true. Again, we'll use R in RStudio, and the command we're going to use is t.test to help us out. Finally, make a conclusion. So if our p-value is small enough, we'll reject our null hypothesis. There may be strong evidence to reject the null, support the alternative. If the p-value is not sufficiently small, we'll fail to reject our null hypothesis. There might not be evidence to reject the null hypothesis. So as a detour before we go into the examples, this t-distribution is what's known as a robust statistical procedure. It's not really affected that much from or by departures from some assumptions, specifically this one, assuming that the variable is normally distributed in the population. Now, depending on which textbook you're using for this class, the authors might make a big deal about this assumption, or they might not. As long as our sample is large enough, this assumption really doesn't matter. So here's what I'd like you to look for. Look for numerical variables with a reasonable distribution of the samples. So no extreme outliers, no unusual patterns. As long as that's the case, then this method tends to work. So, is there sufficient evidence using a hypothesis test to show that the mean hippocampus volume for football players with histories of concussion is less than 6,000 microliters? Let's find out. Our null hypothesis is that the population mean is exactly equal to 6,000. Our alternative comes from that research question, is that the volume's less than 6,000. We'll create a new data set. So I'm going to use the filter function to create a data set that just contains those with a concussion. I'll then do a t-test. My variable is the hippocampus. Mu is 6,000. That's the value from my null hypothesis. The alternative is less than, and then here's the data. Our test statistic is negative 2.2, so that tells me that our sample is about 2.2 standard errors below the null hypothesis. Our p-value is pretty small, less than 0.02, so I would reject this null hypothesis. In other words, there's some pretty strong evidence to show that football players with a history of concussion have a mean hippocampus volume less than 6,000. Now, let's say we want to calculate the confidence interval using this. We can use that same t.test function, but add a new argument, specifically add conf.level, and then the confidence level is returned. One thing I do want to point out is that if you go back to the previous slide, we were using a one-sided hypothesis test here. So remember, this confidence interval isn't the one we're looking for. This confidence interval is just a upper bound on the population mean. For a true confidence interval, use this conf.level option. The other thing I want to point out here is that you get kind of a weird result with the t. So notice that this t is now 48.32. If you don't specify an argument for mu, by default, R will take it to be 0, which is what you're seeing. Let's look at one more example. So radioactive cesium is a waste product of nuclear reactors. As you're probably aware, the Fukushima nuclear meltdown in 2011 released a significant amount of nuclear waste into the Pacific Ocean. In order to measure the effects, fishermen captured bluefin tuna and measured them for radiation exposure. So we're looking at a data of radioactive cesium concentration in the tissue of 15 Pacific bluefin tuna. We've got the min, it's about 5, median's about 10, got 15 observations. Historically, these cesium tissue concentrations were below 2 becquerels per kilogram on average. Now the smallest value that we observed is greater than 4, so there's some pretty compelling evidence already that this is higher than 2 becquerels per kilogram. To be complete, let's do the hypothesis test and verify. So is there sufficient evidence to show that the cesium concentration has increased? Our null hypothesis is that the mean is equal to 2. Our alternative is then that it's greater than 2. We'll feed this data into R, so the variable is cesium. Our mean mu is 2. Our alternative is that this is greater than 2. The data is the tuna radiation data set. So our test statistic is about 11. So we're about 11 standard errors away from what we would expect. There's a very small p-value associated with this. So this is really compelling evidence to conclude the population mean cesium concentration has in fact increased. We can take this and calculate a confidence interval, say a 99% confidence interval. I should replace this 95 with 99, so apologies for that. We're 99% confident that the population mean radioactive cesium is between 8.04 and 12.48. In the next video, we'll talk about how to compare samples of numerical data, specifically how to compare two populations. Have a great day.